All right, we're going to tackle a question on cost curves. As with all these videos, I'll explain what information I'm pulling out as I read through the question and any decisions I make as I'm solving the question. So let's get started on this question. All right. Firm has two factories, an old and a new one. At the old factory, the building's in bad shape, making it hard for workers to do their jobs, and the machines are old, making them rather unproductive. To produce Y units of output at this old factory as cheaply as possible, the firm must use 10 Y squared units of labor and 20 Y squared machines. So we're being told here that we've got this old factory, right? And the labor that we need to produce Y is that 10Y squared, right? And I'll use, or scratch that. Let's use M for machines here. And it's going to take 20 Y squared machines. All right, so I'm keeping track of that on the side so I don't have to dig back through this paragraph. The new factory, building's laid out better, machines are newer. Cheapest way of producing Y units of output at the new factory requires 5Y squared units of labor, 10Y squared machines. So we've got our new factory. So L at our new factory is going to be that 5Y squared, right? And M at our new factory is going to be 10Y squared. All right, we've got one more bit of information, it looks like. So it costs $100 to maintain the old factory, $200 to maintain the new factory, regardless of how much is produced at each factory. So that's telling me about fixed costs there, all right? Because they don't depend on output. So I'm just going to underline those two values so I can spot them easily when it comes time to use them. All right, so part A now. Assume that the wage of a worker is 1, right? So I'm going to say W is equal to 1, and the price of a machine is $2. So my WM here is going to be 2. Write down a function C0Y, given the minimum cost of producing Y units of output at the old factory. Also write down a cost function here for that new factory. Okay, so COY, we've got those fixed costs of 100, right? We have our cost for labor, which is going to be our 10Y squared times our W, right? But I'm going to go ahead and write that out first. That's just W times L as a function of Y. And then we're going to have the price of our machines times our number of machines as a function of Y to capture that part of the cost. Part of the reason that I want to write that out first without plugging in is that in case I make a mistake down the road, the person grading the exam knows that I set up the problem right and I can get more partial credit. All right, so we just need to plug in that information that we handily kept over here in the margin into our equation now. It's going to be 100 plus our wage of 1 times our L of 10Y squared plus our price of a machine of 2 times our 10Y squared, or sorry, 20Y squared for M. All right, so we've got 100 plus 10Y squared plus 40Y squared, so that's 100 plus 50Y squared. I'll put a little box around that as my final answer for C0. Now we just need to do the same thing for our new factory. So Cn of Y, we look back up, we had our fixed cost of 200 at the new factory. So there's my 200 plus WLY plus WM, M of Y. All right, now it's just a matter of plugging in. So we've got 200 plus 1 times 5Y squared plus 2 times 10Y squared. All right, so all of that is going to give me 200 plus 5Y squared plus 20Y squared, so that's plus 25Y squared. There is my final answer for the new factory cost function. All right, so part A done. Now let's move on to part B here. All right. Find an expression Y0Y for the optimal amount of output to produce at the old factory as a function of total output. Okay, so y now is total output, and it looks like we're going to be splitting it between factory old, factory new. So y0 and a ym, or yn for the new one. So let's start on a new sheet of paper here and think through this. So my part B. So I'm trying to figure out this y0, y, right? If I'm splitting my output between two factories, I want to do it so that the marginal cost of those two factories are equal. If they weren't, I could move output from the higher marginal cost factory to the lower marginal cost factory to save money. So what I want is I want marginal costs at the old factory of whatever I'm producing there, right, to equal marginal costs at the new factory for what I'm producing there, right? Okay. So going back to our cost functions from before, right, the marginal cost of the old factory is the derivative of this cost function. So when I write that out, the 100 is going to disappear when I take the derivative, and then I'm going to have 100y, right? So this marginal cost is going to be 100y, and now I want to be clear that that's the old factory's y. All right, marginal cost of the new factory, we go back to that function. The 200 is going to disappear when I take the derivative. My 2, when I bring it down, is going to give me a 50 out in front of the y, and then I'll be left with y. So my new factory, 50 yn is those marginal costs. So this simplifies to 2y0 is equal to yn. Now going back to the question, we want y0 in terms of total y, right? Not in terms of yn. So I need a second equation here, which is just that y0 plus yn should equal our total y, right? I can plug this in for yn, so I've got y0 plus 2y0 is all equal to y. So that's going to be 3y0 equal to y, or y0 is equal to 1/3 y, right? Now the question didn't ask for it, but my guess is that we're going to end up needing yn as well, and it's easy to get that because we know that yn is just 2y0. So I'm just going to go ahead and write over here on the side, in case I need it, that yn is going to be 2yo, which is going to be 2/3y. Okay? So 1/3 of our output at the old factory, 2/3 of our output at the new factory. Okay, part C now. Find an expression for total cost for the firm of producing y units of output, cy, assuming the firm splits output optimally across factories. Okay, so what we had from part B was already our optimal split of output. So in part C, right, we're thinking about total costs. Those are going to be the costs at our old factory of producing 1/3 y, right, plus the cost at our new factory of producing 2/3 y. Okay? And so we just have to go back to those original cost functions for our factories that we found earlier, right? That 100 plus 50y squared, 200 plus 25y squared. Only we're going to plug in for our y's here. This one's going to be 1/3 y, right, in the old factory. This one's going to be 2/3 y in the new factory. All right, so here we go. My old factory cost function, I had 100 plus 50y squared, so that's going to be 50 times 1/3y, all of that squared. All right. My new factory was 200 plus 25y squared, but we're replacing y with that 2/3 y. So I've got my 100 and my 200 are going to add together to give me a 300 out front. This is going to give me 50y squared over 9. Say 50 over 9y squared. And then here we're going to have 4 over 9 times 25, so that's going to be 100 over 9 y squared. So we can clean that up a little bit more. 50 over 9 plus that 100 over 9. This gives me 150 over 9 y squared. Right? Could leave it like that, or I could make it even a little bit nicer for myself by saying that that's 300 plus, now these are both divisible by 3, so that would be 50 over 3 y squared. Right, so there is my overall cost function. All right, let's head on back to the problem, see what we need to do now for part D. Assuming the firm splits output optimally across factories, draw a graph giving the firm's average total costs, all right, as a function of y. We also want average variable costs as a function of y, and we want marginal costs as a function of y. All right, so we've got our cost function. Let's keep that up at the top here. And so I need to graph in part D. We need average cost, we need average variable cost, we need marginal cost. All right, well, average cost is just going to be cost divided by y. So when I look up my cost function, that's going to be 300 divided by y plus 50 over 3 divided y squared divided by y, which is just going to leave me with 50 over 3 y. All right, average variable cost would be my variable cost divided by y. Well, I've already figured that out because I got that with average cost. This first part was my average fixed cost. The second part there was the average variable cost. That's the part that came from the term that varied with y. So that's just going to be my average variable cost, that 50 over 3 y. Now my marginal costs are going to be the derivative costs with respect to y. So going back up to my cost function, the 300 is going to disappear when I take the derivative. The 2 is going to come down, give me 100 over 3, and I lower my power by 1, leaving me with y. So there's my average cost, average variable cost, marginal cost. Those are now what I need to graph. All right, so let's go ahead and make that graph. So y on the horizontal axis, dollars on the vertical axis here. All right, I'm going to start with whatever looks simplest to me, which is average variable cost, 50 over 3 y, right? So that's a straight line. Oops. There's my average variable cost, all right? Now I look at marginal cost, also a straight line, just twice as steep, right? So here comes marginal cost. All right, now for average cost, this one's a mess, right? I've got a 300 over y plus a 50 over 3y. So this term's getting smaller as y gets bigger. This term's getting bigger as y gets bigger. But I know that those average fixed costs are going to drive y up toward infinity, or costs up toward infinity when y is getting close to 0. And I know they're going to get close to 0 as we move out to big Y. So I know that I want this curve to come down, hit its minimum at the marginal cost curve, and then approach my average variable cost curve. All right. So the question didn't explicitly ask for it, but let's go ahead and put slopes on for our average variable cost and our marginal cost because we can, right? So slope for average variable cost, 50 over 3. Slope for marginal cost is that 100 over 3. All right, let's move on to the final part here, part E. Okay. Suppose the wages for workers increased, but the price of a machine stayed constant. How would this change the optimal allocation of output across factories? Be certain to fully justify your answer. All right, so let's think about what this is going to do, right? If I go back to my original part A, that's where wages were coming in, right? So wages impacted this 10y squared right here, and they impacted this 5y squared right here, all right? So I'm actually going to do this mathematically because I think it's going to be quicker than if I try to write this out with a big long explanation, right? The way I'm going to think about this is we know that marginal cost at the old factory should equal marginal cost at the new factory, right? That's how we solved the earlier part of the problem. And so when I go back to my cost functions here, I'm going to leave that w in there as it is, right? So I'm going to do w 10y squared plus wm, or 2 times 20y squared, all right? So when I take the derivative, I'm going to have 10wy plus my 40y that's going to come from that 40y squared term, right? Oops, that should be 80y. Okay. On the new factory side, if I go back to that equation, right, that would have been 200 plus w times 5y squared plus 20y squared, right? So I'm going to have that 2wy when I take a derivative. Right? So that's going to be, or sorry, 10wy when I take the derivative. Right? And then I'm going to have my 20 over here. That's going to become 40y when I take the derivative. All right. And I made a slight mistake earlier that I just realized, right? I didn't bring down the power when I took the derivative here, so that should have been 20y. Okay. All right, so this is y0. These are yn's. We need to be careful that we keep track of that. Okay. All right, we can still take out a y0 here, right? And that's going to be 20w plus 80 is equal to yn times 10w plus 40. All right, so how is this going to change my location of output? Well, I can move this over here to slightly simplify things. That's going to give me a 10w plus 40 over 20w plus 80, right? All of that times yn. And so if I pull out some common terms here, we can see if we can simplify this a little bit further. So I can pull out a 10 on the top. That's going to leave me with w plus 4, right? I can pull out a 20 on the bottom, which is going to leave me with a w plus 4, right? And so those w plus 4s are actually going to cancel out, and I'm left with 1/2 yn, right? So w doesn't matter here. We're going to split the output the same way, right? So w doesn't impact how we allocate output. Right? And so there we are. We're done.